Okay, so we are going to be doing story problems in 4.7 that are going to be using rational equations. So in 4.5, or was it 4.6? No, I can't remember. Yeah, 4.5, we talked about rational equations and how to solve those. And so now we're going to just have some story problems that we're going to be dealing with here. So one type of problem that you're going to find are what we call work problems, because it's either, things working together or against each other. And I'll show you what I mean by that. So on this one, this is a working together problem. So a water tank can be filled in 5 minutes and emptied in 7 minutes. If the drain, oops, this is an against one. Okay. If the drain is accidentally, whoops, I can't see all of my thing here. Okay. If the drain is accidentally left open when the tank is being filled, how long does it take to fill the tank? All right. So on this one, so what I meant by working against is it's like, okay, you're trying to fill something up, but at the same time, it's trying to be emptied out. And so that is, what we're kind of looking at here. And so when we're taking a look at this, we're trying to figure out how long it takes to fill the tank. All right, so I'm going to say that's what X is. X is, was it minutes? Yeah, minutes to fill the tank. All right, and then we can see that we have something here where it's like, okay, we are doing, one job. So we're going to be having some fractions here. One job, and the water tank can be filled in 5 minutes. So we're going to say it can do one job in 5 minutes, right? But it can be emptied in 7 minutes. So since we're going to be emptying it, we're going to use subtraction. And so then we can do one job in 7 minutes. And then the last thing here is, what that is together. And so one job together. And so that's kind of what we're having here. So that X is how many minutes it's going to take to fill the tank when these things are happening. Okay, so like we talked about before, when we're solving these types of equations, we need to find the LCD because we need to multiply each part by the LCD. So let's go ahead and let's see. It's not picking that one. All right, so we are going to figure out what that LCD is. And we can do that by multiplying like all of the bottom together there. So 5 times 7 is 35, times X is 35X. And so that's what we want to multiply each part by. So put 35X over 1, and then we'll do that to all of these different parts. And then, all right, and so now we need to kill off the denominators. All right, so I can see on here that in this first one, 5 divides into 35 7 times, right? And I'm trying to get rid of that denominator, right? Now it's just a 1 because I just divided that in. Here, similarly, 7, right, can go into 35 5 times and into itself once. And then here, the X's divide out. And so let's see, what are we left with here? So 7x times 1, so that's going to be 7x, minus 1 times 5 times x, so that's 5x, and then equals 1 times 35, which is 35. So now we'll subtract those. We'll have 2x equals 35. And then we just need to divide both sides by 2. Now, usually on this, if it comes out to be a fractional answer, it'll usually have you actually write it as a decimal, and they'll tell you what place value you need to round it to. All right, but on this, if we do 35 divided by 2, we get 17.5. And make sure you put your label on it, and that would be minutes. All right, so that's how long it's going to take to fill the tank. So, and it makes sense because remember, like if it takes 5 minutes to fill it up, if it's plugged up, right, if the drain isn't open, then we expect that it will take a lot longer to fill up if most of it's being emptied out as it's filling up. So that seems like a reasonable answer.
So that means that they finally realized that the plug was not in, and they put it in, and it was 17.5 minutes from the moment they started to fill it in to the moment that it actually filled up, including the time to plug it.
Well, this would be before they plugged it. So you know how like if you have, like sometimes if you have just a small drip in your sink, or you know, like if it is slow, you know, if it's emptying kind of slowly, but you're still filling it up, at some point it will fill up, you know, faster. And so yeah, so this is, they didn't know that it was plugged or unplugged. And so this is how much time it would take if that was the case. But if they plugged it up, then it would have only taken 5 minutes. So okay, so all of these are going to be involving these fractions, you know, these work problems. And remember, we're always kind of talking about one job can be done in the time that's given to us here. Okay, so let's look at this next one. Amy can clean the house in 9 hours. When she works together with Amelia, the job takes 4 hours. How long will it take Amelia working alone to clean the house? All right, so let's just write some stuff up here. So I'm going to put Amy, and then I'll put Amelia, and then together. All right, and so let's look at Amy's part. So again, we're thinking about it's going to be, you know, the top fraction is going to be talking about one job, right? That whole job in a certain amount of time, right? So I'm just going to write this over here just to make sure we're kind of seeing that. Okay, so with Amy, she can do one job in 9 hours by herself. All right. And then the next says when she works together with Amelia, so that's going to go in this part here, it takes 4 hours. So together they can do one job in 4 hours. Okay. And so what we're trying to find is how long it would take Amelia working alone. So one job in X hours. And since they're working together this time, right, not against each other like the last one, as they're working together, we'll put a plus sign in between these. And so we'll have however much Amy can do plus what Amelia can do equals what they can do together. Okay, so what would our LCD be on this?
9 times 4, 36.
Yeah, 36, and don't forget about your X too.
36x.
Yep, 36x. So let's write that over here. So 36x over 1. So we're multiplying every single part by that. All right, and now we will just, you know, simplify these up, kill off the denominators that we can, because makes it so much easier. I mean, look back up at the, you know, the last one, you know, having those fractions in there just, I mean, it looks hard to do, but once we get rid of them, we're like, oh, I can totally do that. All right, so let's try this one here. So we want to get rid of the 9. So 9 divides into 36 4 times. Here, we got an x on the bottom that can divide out with that x on the top. And then 4 can divide into 36 9 times. So let's see, let's write down now what we have left. All right, so we have 4 times x times 1, so 4x plus, and then we got rid of that x. It almost looks like I have the x there, but that is gone. All right, so we just have 36, and then equals 1 times 9 times x, which is 9x. All right, and now from there we're like, okay, that doesn't look so bad, right? So let's subtract the 4x over to the other side. That will give us 5x, and then I have 36 here, and then to get x by itself we need to divide by 5. So what is 36 divided by 5?
That would be 7 point something.
Yep, 7.2. All right, and then again, make sure you have your units or labels on that, which we're talking about hours. And then word problems need word answers. So 7.2 hours. Amelia can do the job alone. Or maybe it would have been better to
She's
say.
quicker than Amy. we need to hire Amelia.
Yes, exactly. But we've got them both.
Yeah.
So, yeah. Let's see here. It just looked really weird the way that ended up. But yeah, so, and it makes sense as an answer here because remember, together they should be able to do it in the fastest time. And we came up with 4, or there was 4 hours, right, together.
Mm-hmm.
And so that number that we come up with better be bigger than 4, because if it's smaller, then, you know, then why would...
she's Speedy Gonzalez.
Yeah, and why would you even want Amy's help? If you can do you can do it faster than the two of you could do it together. So... yeah, so just make sure you're kind of thinking about those answers and if they make sense on this one. Okay, so let's try this one. See if you can help get it set up here. Okay, Mackenzie and Lars work on a landscaping crew. They can complete the landscaping job in 4 hours if they work together. Mackenzie generally takes 6 hours less than Lindsay. Okay, so this is different. It's not just 6 hours. It's 6 hours less than Lindy. How long would it take Mackenzie to complete the landscaping job if Lindy calls in sick? All right, so maybe we'll use an M to stand for Mackenzie. All right, so we'll say Mackenzie time working alone is what we're trying to find. Let's see. Yeah. Well,
So this one will be with a minus because Lindy calls in sick, so she's not in to help.
Yeah, so we first have to figure out what it would be. So we got Mackenzie because we know how long it takes them to work together. So we actually have to figure it out first, you know, so we can kind of see what happens here. So we know stuff about Mackenzie's time. We know stuff about Lars's. Oh, wait a minute. It says Lars and then it says Lindsay. Well, or Lindy. Let's put that Lindy up here. Lindy. Okay. Sorry, I don't know how the different name. Okay, so Lindy and then together. Okay, so this is what we're looking for is Mackenzie's time. So we know if we go with this first part here, right, this is the time it takes them working together. And so that together time is going to be like equals, right? They can do one job together in 4 hours. Okay. Now, we don't know, exactly how long it takes Lindy. We just know that it takes Mackenzie about 6 hours less. All right, so we don't know what Lindy is, so I'm going to put that Lindy can do one job in X hours. And then we have to think about that relationship that they're talking about here between Lindy and Mackenzie. Whoops, I was going to put...
so there has to be a plus, X plus.
Yeah, I'm going to put it and change this to X because I have it here. So if it says she takes 6 hours less than Lindy.
So X minus 6?
Yeah, so whatever, however much time it takes Lindy, we're going to minus 6 off of that. Okay. And then this is, since it says they're like working together, that makes it a plus sign in between there. All right, and then these, our common denominator, or LCD on this, remember everything needs to be accounted for. So we need 4, we need X, and we need X minus 6. So all of those. We can't just use that X without the X minus 6 because it's not connected by multiplication there. So we have to think of that as one separate thing by itself. Okay, so let's look at this one then. So if we multiply each part by that, 4x times x minus 6, and then the same thing here, 4x times x minus 6, and 4x times x minus 6. And then like we've done before, we're just trying to kill off the denominator, so I want to get rid of that x plus 6. And I see it has a common factor there on the top. I want this x to divide out with this x, and this 4 to divide out with that 4. All right, so we got rid of all the denominators. There's just a 1 on the denominator now. Okay, so let's see. What do we have left then? So here for... Yeah, go ahead and tell me.
4x on the first one,
on
Mackenzie. The one on Lindy.
Can you read that?
I think is 4x minus 6.
Yep.
And then on the one together, we get rid of the 4. So it's x minus 6.
Yeah. All right, and now let's just distribute through to make it easier for us to solve this. So when I distribute that, I get 4x minus 24. Now this time I have to distribute the x, so x times x is x squared, and then x times negative 6 is negative 6x. Okay, now on this one we've got to be kind of careful, right? Because we've got an x squared, and so when we have something like this that we're trying to solve, we've got to get everything over to one side of the equation and set the other side equal to 0 so that we can factor to solve it. That's what we're going to be doing here. And maybe just before we do that, we didn't talk about the excluded values on the last one, but let's make sure that we, think about that on this. So we can't have a 6 in the denominator, or it's going to make this one 0, right? So x cannot be 6, and x cannot be 0, because on this one it would make that. Right? So it can't be 6 and it can't be 0. All right, so since this x squared term is already positive, I'm going to choose to move the stuff on the left over to the right. So if I combine those together, I get 8x, right? And so I'm going to subtract that 8x over here. And then I need to add the 24 over. And then let's see what we end up with here. So we have 0 equals x squared, right? And then we got negative 14x, and then plus 24. And so now I need to think about how I can factor this to solve it. I don't know if I'm going to have enough room here, but we'll try. All right, so since the leading coefficient's 1, I can go straight to these parentheses.
12 and 2.
Yeah.
So minus 12 and minus 2.
Yeah, minus 12 and minus 2. All right, and then when I set both of those equal to 0 and solve, right, so we have x minus 12 equals 0, and then x minus 2 equals 0. And so if I add the 12 over, I get x equals 12, and here I get x equals 2. Okay, so neither of those are the excluded values, but we need to think about kind of what's happening here, right? So if we said, you know, that if we look at this one that says x equals 2, well, remember we said that Mackenzie's, you know, it takes her 6 hours longer. So if I put that, you know, 2 in place of the x here, 2 minus 6 gives me a negative 4 hours, right? Mackenzie can't do work in a negative amount of time, so that one doesn't make sense for what we're talking about. Is that clear?
Yes, correct. Yeah.
Okay, so you've got to think about those solutions and make sure, you know, you're thinking if that works or not. Sometimes they come up as these excluded values already, and so you know you can't have them. But on this one, it's a little different. You have to think through it a little bit differently. And so x equals 12. Remember, that was how long it took Lindy, right? So it takes, let's see, so Lindy takes 12 hours. And so what does that mean for Mackenzie then?
6.
Yeah, so we have to subtract 6 off of it. Right, it takes 6 hours. And then it did want us to know how long it was going to take Mackenzie. So that's what on the homework, make sure you put that in. It might not even ask what Lindy's time is, but it gets kind of confusing because you come up with that 12 first, and so a lot of times people just automatically put 12 in for their answer, but notice that it wanted Mackenzie, so we need to do that subtraction before we say that's our answer. Okay, so again, that's a good reason why it's good to make sure you write out what it is, you know, those numbers are meaning for your story problem. All right, any questions that you can think of on these word problems? Or sorry, word problems that are work problems.
No, so far they make sense.
Okay, yeah, and remember, since we are dealing with rational equations, right, we will have these fractions in them, so you'll definitely make sure that you're making fractions when you're doing this, but it's always one job over the amount of time that they can do it. Okay, so these are a little bit different, but we saw something similar to this in Module 2, and so now we're going to be kind of building on that idea. And remember, in Module 2, we dealt with systems of linear equations where we did like the substitution and the elimination method. And so we're going to have to use some of those on here.
This is kind of ironic, but this was the one thing that I could never make work.
Oh, well, let's figure it out right here, right now, right? Make sure. Because the part that usually, I'd say where students mess up on this is because when we're dealing with rate, so we are dealing with the formula distance equals rate times time. But this rate is not given to us. Like a lot of times people try and put that 6 miles per hour in there for the rate, but that's just the speed of the wind, right? Not the speed of the helicopter, which is what we're trying to find on this one. So, all right, so let's read through it and then I'll kind of explain a little bit more. A helicopter travels 270 miles with the wind in
It's positive.
Say that again?
So that part is positive because it's west the wind, so the wind is on his favor.
Yep, that's right. And then in the same amount of time, it can go 180 miles against the wind. Okay? And then the speed of the wind is 6 miles per hour. Find the speed of the helicopter with no wind. Okay, so this is the part that I want to make sure is clear. And it's how we get the rate. Because the rate, I think like you were saying, we're going to have like a plus or minus on that. Because our rate is made up of the speed of the helicopter, of the plane, of the boat, whatever it is that we're dealing with, right? The speed of that vehicle, plus or minus like the wind speed, right? Or if it's a boat, then it would be the current speed of the current. Okay, but you always have to have, like on this one, it's the helicopter. I'll put heli for helicopter, right? Helicopter speed plus or minus the wind speed. So when we're setting this up, I kind of set it up in a chart last time too, just because to, organize that information. Sometimes it's helpful to have that. All right, and then we're dealing with two different things here, right? So we know that there's with the wind, oh my goodness, and against the wind. All right, so let's see what we know here, right? So let's just start with the top one, with the wind. So do we know the distance it can go with the wind?
170 miles.
Okay, so let's put 270 there. Okay, do we know the rate? So remember, the rate is...
It can go... No, we do not know the rate. Well,
so what we know part of it, because remember up here, rate is made up of two things here. We don't know the helicopter speed, right? That's what we're trying to find. So maybe I'll put that as H. And then remember, it's the helicopter speed plus or minus the wind speed. Do we know the wind speed?
6 miles per hour.
Yeah, and so here we've got to decide, is that going to be a +6 or a -6?
Well, the speed of the wind.
Because we're going with the wind.
With is positive.
Yeah, so we'll put +6. All right, and then let's go down here. What about the...
distance is the same. No.
Nope.
You can go...
The time is the same. So, yep, you can go 180. And our rate this time is going to be the helicopter speed
minus
the wind speed, so -6. All right, now this is the part that's different about what we did before. So if we take this distance equals rate times time problem, because all we know is it is in the same amount of time. I don't know like the number of hours or anything to put here. I just know these guys have to be the same. So let's solve this distance equals rate times time for time. Let's get time by itself, kind of like we did in the last section where we solved those. So let's divide both sides by r. And when we do that, right, we can see that time is the distance divided by the rate. Well, we got something here for distance, so that's going to go on the top, and then the rate is going to go on the bottom, h plus 6. And then similar down here, right, we got to set it up with distance divided by rate, so our distance is 180 divided by our rate, which is h minus 6. right? And then we know that it has to be the same time. So when it says same in math, what does that mean?
Equals?
Yeah, they got to be equal to each other. All right, so when I set up this equation to solve, I'll have 270 over h plus 6 equals 180 over h minus 6. And now we're going to solve these like we've done the ones up, on top and what we did back in 4.5. So our LCD, whoops, I don't know why I put X there. Let's change that to an, probably because I'm just used to putting X's. All right, that should be an H. We don't want two different variables there. That was just my mistake on there. There we go. So now we want to make sure that we have our common denominator, or LCD, which is going to be h plus 6 times h minus 6. And that's what we need to multiply both sides by. So let's take this. So we got h plus 6 times h minus 6. Where this is not writing very good today. And then here, same thing, h plus 6 over h minus 6. And again, these are over 1. So this is helping us to kill off the denominators, right? We cannot solve for this, when it's in the denominator. So we want to get rid of it. So that h plus 6 divides out with that h plus 6. And then over here, our h minus 6 divide out. And so then we can see, all right, what am I left with? Well, I'm left with 270 times h minus 6 equals, then over here, got 180 times h plus 6. All right. Any ideas of how we might go about solving from here? What do you think would be a good next step?
Well, normally I would say if it is multiplying, we need to divide.
So so you want to try and divide that 180 over to the other side. Is that what you're saying?
Yeah, I was thinking in that principle that you do the opposite.
Uh-huh.
Because it's not like the ones that we can do minus and move it to the other side.
Yeah, I mean, we could distribute it through, but let's go ahead, and I like your idea of this. So let's go ahead and divide this side by 180. And notice that we're choosing the one that is the smaller number. That would be the one we'd want to divide by because we've got numbers on both sides there. All right, so when I do this, I'm saying, okay, those 180s divide out, and then 270 divided by 180 is 1.5. I'm going to have to come over here. So I'm going to have 1.5 times h minus 6 equals just h plus 6. All right, so now let's distribute that through and see what we come up with here. So 1.5h minus, so what's 1.5 times?
Be 9.
Uh-huh. And then equals h plus 6. All right, so let's subtract this h over here, like we're subtracting 1h over. So that just gives me 0.5h. And then I need to add the 9 over to the other side. And that is going to give me 15. All right, so we're almost done. Now let's just divide both sides by 0.5. And then what is 15 divided by 0.5?
3, but there is a point in there somewhere.
So, yeah, so 30, right? Because you're right, because we have 15 divided by 5 would be 3, but then we have to move that decimal place over 1. So h equals 30. So 30 what? What is it that we were finding?
The speed of the helicopter.
Yeah, speed of the helicopter with no wind. So make sure we put miles per hour, right, is the speed of the helicopter. All right. Okay. So yeah, we've had to make, we had to make 2 different equations here. And then we set those equal to each other because it said in the same amount of time. So, okay. Then this last one here, right? We've got Barbara can bicycle 69 miles in the same time. All right, let's see. So Barbara, 69 miles, the same time as it takes her to walk 9 miles. She can ride 10 miles per hour faster than she can walk. How fast can she walk? All right, so this is we're still dealing with this distance equals rate times time. All right, now we're not dealing with some kind of like a with the wind or against the wind. It's not talking about that on this one. This time we're comparing, the speed of her bicycle to how fast she can walk. But let's set this up again. So distance equals rate times time. And so we're going to have our bike, and then walking. All right, so let's see what we can fill in here, right? So we know this is going to be in the same amount of time. So just like we did up here, right, we had to solve for time, so we're going to still be dealing with that distance divided by rate is our time. So we got to think about that when we're dealing this. So we should be able to put stuff in our distances and our rates. So let's see what we can put there. All right, so do we know the distance of biking?
69 miles.
Okay. And then what about the rate? Well, let's look at it. She can ride 10 miles an hour faster than she can walk. So when it ends with this word walk, like whatever it ends in, that's what your variable is going to be. Okay, and so I don't know how fast she can walk. I just know that she can also bike 10 miles an hour faster. So however fast she can walk plus 10. Does that make sense?
Yes.
Okay. And then the walking distance, whoops, I forgot to put that in, is 9 miles. Okay, so like I said, it says the same amount of time, so we need our distance divided by our rate. So we're going to have 69 over x plus 10, and then 9 over x. And then these have to be the same, so we've got to put those equal to each other. So 69 over x plus 10 equals 9 over x. Okay, and again, we got to multiply everything by the LCD, and our LCD on this is both of these denominators. So I need to multiply this by x times x plus 10. I'll put that over 1, and then the same thing here. Right, I'm just looking at those denominators, x times x plus 10. And then let's kill off the denominators, so that x plus 10 divides out with that, and then this x divides out with this x, and so we are left with 69x equals, and then I've got this 9 out here, And I've got to distribute that through our x plus 10. Okay, so let's distribute that through and see what happens here. So 9x plus 90. All right, so let's subtract our 9x over this way. So that will leave us with 60x equals 90. And then if we divide both sides by 60, what are we left with?
1.5, I think.
Yep, 1.5 what?
So I divided miles by miles. So it's miles.
Well, but look at what our question is.
How fast can she walk?
Yep, and so
1.5.
Mm-hmm. And then since it's talking about speed, how fast, that'll be miles
per hour.
Yeah. So she can walk, right, is, let's see, 1.5 miles per hour is how fast she can walk. All right, and that's what it's asking us, right? If it asked us, let's see. No, wait a minute. Yeah. If it asked us how fast she could bike, it would be 1.5 plus 10, right? And we'd put that. But this is what it's asking for, so we are done. What is that one?